Hello everyone, this is Natra Saram Findala and this is my AAT concept video for DMS and my roll number is 2197 from CSA section and my topic is graphs. What is a graph? So a graph is a mathematical object that is used to model different situations of the same process like linked list, trees, flowchart of a program, structure chart of a program, finite state auto menu, city map, electrical circuit, course curve. Definition. A map is a collection, non-implicit, of vertices and edges. So what are vertices? Vertices can be names and properties, and edges connect to vertices can be labeled and can be directed. Adjacent vertices. If there is an edge between them, that is called an adjacent vertices. Example, here we can see graph 1, A, B, C, D, and the vertices are A, B, C, D. Edges are A, B, A, C, B, C, and C, D. Same graph in another way, A, B, C, D, and the vertices are A, B, C, D, and the edges are AC, BC, AB, and CD. Director graphs and undirected graphs. There are there are two basic types of graphs, directed and undirected. In undirected graph, the edge is symmetrical. Example, if A and B are vertices, AB and BA are one of the same edge. Graph 1. The above is undirected graphs. In indirected graphs, the edges are oriented. They are beginning with an end. Thus, AB and BA are different edges. Example 2. Examples for directed graphs. Graph 2 and graph 3 are different graphs. Some definitions of basic graphs concepts differ slightly depending on whether we talk about directed or undirected graphs. Path. A path is a list of vertices in which successive vertices are connected by edges. Example, some paths in graphs are ABCD, AC, BACD, AB, DCB, CBA. Some paths in graph 2 are DAB, ADAC. That DAB is a path in a graph, however, ADAC is not a path in graph 3 because AC is not an edge. The edge is CA, simple path. No vertices is repeated, so that is called simple path. Cycles. A cycle is a simple path with distinct subjects where the first vertex is equal to the last. Example, in cycles in graph 1, CABC, CBAC, CABCA, ACBA, BACB, BCA, BABA is not a cycle because the edge AB is same as BA. Cycle in graph 3, ADA, DABD. A graph without cycles is called acyclic graph. Loop. An edge that connects the vertex with itself is called a loop. Connected graph. And the example below is a loop and connected graphs. There's a path between each two vertices. Graph 1, graph 2, and graph 3 are connected. Disconnected graphs. There are at least two vertices are not connected by a path. Example for the disconnected graphs. Graph 4 and graph 5 are disconnected graphs. Vertices ABCD, edges ABCD, and graph 5. Edges are ABAC, vertices are ABCD. Isomorphic graphs. Two graphs which contain the same number of graph vertices connected in the same way are said to be isomorphic. Formally, two and with graphs or vertices said to be isomorphic if there is a parameter of such that in the set of graph edges G of E, if is a set of graph edges. Two graphs G1 and G2 are said to be isomorphic. If the number of components, vertices and edges are same, the edge connectivity is retained. Note, in sort of two isomorphic graphs, one is a weakened version of the other. An unlabeled graph also can be thought of an isomorphic graph. There exists a function f of vertices of G1 to vertices of G2, f of v of G1 that employs v of G2. Such that case, if a bijunction both one on one and on two case. Two, if f preserves adjacency of vertices, if the edge uv e of G1, the edge f of u, comma f of v belongs to G2, then G1 is equals to G2. Note, if G1 G2 then G1 equal G2, then v of G1 is equals to v of G2. Mod e of G1 is equals to mod e of G2. Degree sequence of G1 and G2 are same. If the vertices V1, V2, Vk, so on Vk of cycle of length k in G1, then the vertices f of V1, f of V2, f of Vk should form a cycle of length k in G2. All the above conditions, all the above conditions are necessary for a graph G1 and G2 to be isomorphic, but not sufficient to prove that graph are isomorphic. G1 and G2 is only if G1 minus is equal to G2 minus, where G1 and G2 are simple graphs. G1 G2 is adjacent matrix of G1 and G2 same. If G1 is equal to G2, if and only if corresponding subgraphs of G1 and G2 obtained by deleting some vertices in G1 and their images is graph in G2 are isomorphic. Example, in the graph G3, the vertices W has only degree 3, whereas all the other graphs vertices as degree 2. Hence, G3 is not isomorphic to G1 and G2. Taking components of G1 and G2, you have here G2, G1, G2, hence G1 is equal to G2. Euler graph. And closure graph is a graph G containing all the edges of G is called a Euler line in G. A graph containing Euler line is an Euler graph. We know that a walk is always connected. Since the Euler line, which is a walk, contains all the edges of the graph, and a Euler graph is connected except of any isolated vertices the graph may contain. As isolated vertices do not contribute anything to understand of Euler graph, it is assumed now onwards that Euler graph do not have any isolated vertices and are thus connected. Example, consider the graph shown in the figure. Clearly V1 E1, V2 E2, V3 E3, V4 E4, V5 E5, V3 V6, V7 V1 in Euler line, whereas the graph shown in P is non-Eulerian. Eulerian path is a path in graphs that visits every edge exactly once. Eulerian circuit is an Eulerian path which starts and ends on the same vertex. These are some examples. A graph is called Eulerian if it is Eulerian cycle and called semi-Eulerian. If it has Eulerian path, the problem seems similar to Hamilton path, which is a MP completed no completed program for general graphs. Fortunately, we can find whereas a graph has Eulerian path are not in polynomial time. In fact, we can find in O v plus c time. Following are some interesting properties of undirected graphs with Eulerian path and cycle. We can use these properties to find whether a graph is Eulerian or not. Eulerian cycle. An undirected graph has a Eulerian cycle if following two conditions are true. All vertices with non-zero degree are connected. We don't care about vertices with zero degree because they don't belong to Eurasian cycle or path. We only consider all edges. All vertices have even degree. Eulerian path. And undirected graph has Eulerian path if two conditions are true. Same as condition A of Eulerian cycle. If zero or two vertices have odd degree and all the other have even degree, note the only one vertices with odd degree is not possible in an undirected graph. Sum of all degree is always be in an undirected graph. Note a graph is not no edges is considered Eulerian because there are no edges to traverse. Hamilton graph. A cycle passing through a vertices of a graph is called Hamilton cycle. A graph containing a Hamilton cycle is called Hamilton graph. A path passing through all the vertices of graph is called Hamilton path. And a graph containing a Hamilton path is said to be traceable. Examples of Hamilton graphs are given in figure. If the largest of a Hamilton graph is dropped, we get a Hamilton path. However, a non-Hamilton graph can be used Hamilton path. That is, Hamilton paths cannot always be used to form a Hamilton cycles. For example, in figure 1, G1 has no Hamilton path and so no Hamilton cycles. Z2 has a Hamilton path V1, V2, V3, V4, but the no Hamilton cycle. While G3 has a Hamilton cycle V1, V2, V3, V4, V1. A multi-graph or general graph is a Hamilton if and only if underlying the graph is Hamilton. Because if the G is Hamilton, then the Hamilton circle G remains a Hamilton cycle in the underlying graph of G. Conversely, if the underlying graph of the G is Hamilton, then the G is also Hamilton. We can change from a non-Hamilton graph to a Hamilton graph through some stages of procedure. For example, the non-Hamilton graph G1 above is followed by Hamilton graph G2. Since supergraphs of Hamilton graphs are Hamilton. Once Hamilton graphs are reached in the procedure, all the subsequent supergraphs are Hamilton. Thank you.